everyone. Today we are going to be talking about the nature of light. So let's first start with the speed of light. There was a Danish astronomer in 1675 who measured the first speed of light, and he found that the orbital period of Io around Jupiter fluctuated by a few seconds, and that depended on the position of Earth in its orbit around the Sun, and he realized this was due to the finite speed of light. Using some um, tricks, he calculated the speed of light to be 2.0 times 10 to the 8th meters per second, which is a bit off from what we know it, but it's still a good starting point. Then we have someone else who came in, Armand Fizeau, in 1849, who made the first successful terrestrial measurement of the speed of light at 3.15 times 10 to the 8th meters per second. Still a bit off, but it's getting closer. And what it means by terrestrial measurement, it wasn't based on the planets moving around or the moons. It was actually an experiment here on Earth. Then we have French physicist Jean-Bernard Leon Foucault. If I'm pronouncing that wrong, I do apologize. He modified this apparatus that the last person used, and he found that the speed of light was 2.898 times 10 to the 8th meters per second. Then we have Albert Michelson. He used Foucault's method and refined the technique so well to find the speed of light to be 2.99796 plus or minus 4 times 10 to the 8th meters per second. Now, today we know that the speed of light is 2.99792458 times 10 to the 8th meters per second, or roughly 3.00 times 10 to the 8th meters per second if we round to the third digit there. Okay, so this is a process that has been developing for the past few hundred years, as you can see, and we have found that the speed of light is some finite value. Now, we know this speed of light to be in a vacuum. Okay, so that speed of light that we just found is the speed of light in a vacuum. What happens when it is in matter or some sort of material? Okay, so the speed of light is less in material than in a vacuum, so it slows down, and that's because the light interacts with the atoms in the material. So the speed of light depends strongly on the type of material, since its interaction varies with different atoms, crystal lattices, and other substructures. Okay, so we've got light that's kind of trying to go one direction, and then it gets slowed down, maybe has to bounce around a little bit through the crystal lattices and so forth to continue. So we define a constant of a material that describes the speed of light in it as its index of refraction. This is our index of refraction right here. And it is equal to the speed of light in a vacuum divided by the speed of light observed in the material. Okay, so this is speed of light in vacuum divided by the speed of light in a material. Okay, so this is a fraction, and as we know, the speed of light is greater, the speed of light in a vacuum is greater than the speed of light in a material. Okay, so C is going to be greater than V always. Okay, this is going to always be true, meaning n is always going to be greater than 1. Okay, that's what this means. So let's look at a few examples here. Here are the indices of refraction in various different mediums for light with a wavelength of 589 nanometers in a vacuum. Okay, so these are measured values. So we have a few gases here: air, carbon dioxide, hydrogen, oxygen, and as you can see, they are all greater than 1. Their index of refraction, remember that's what the N means, index of refraction is all greater than 1. Okay. Same thing when you get to liquids. They get even higher here. They're quite a bit higher than these gases that we have found. So we have a few listed here. Then we have some solids. They can get even higher, up to diamond here, which is 2.419. Okay, so again, speed of light in matter is always less than c, okay, which is in a vacuum, which is why n is always greater than or equal to 1. It would be equal to 1 if it is traveling through a vacuum. All right. All right, let's look at an example real quick. This states, calculate the speed of light in zircon, a material used in jewelry to imitate diamond. So we want to find V in zircon. So what is N of zircon? We need to go back to our table here and find zircon. Here it is, 1.923. 1.923. And we're trying to find the speed of light. So we know that N is equal to C over V. Therefore, V is equal to C over N. Excuse me. We're going to use the approximation for C. So 3.00 times 10 to the 8th meters per second. And we'll divide that by our N value, 1.923. Let us put that into our calculators. So 3 times 10 to the 8th divided by 1.923, and we get a speed of light of 1.56 times 10 to the 8th, and that's in meters per second. All right, so this is our speed of light in zircon. One thing we should also notice is that N has no units. This is because it is a ratio. So as you can see, if we divide a speed by a speed, we're going to have something that's unitless, and this is a ratio. So again, N has no units. All right, so let's talk about the ray model of light. So light can travel from a source to another location through a few different processes. It can go through empty space, like the sun to the earth. It can go through a media, like glass, air, water, something to an observer. It can also go through a reflection, like a mirror. So the light rays from maybe outside are coming through, hitting a mirror, and bouncing back to the observer. Okay, so this ray model describes this path of the light that the path that the light takes as straight lines. So rather than our typical, um, light travels in waves, and waves we think of as little squiggly lines, I guess we can say. We're going to describe these now in straight lines, okay? Now, The light may change directions when it interacts with some sort of material, where its path is described by geometry and simple trigonometry, which is called geometric optics. That we will get to next time, but just to kind of preface this, our light will change directions based on the material. Okay, so I'm going to stop here and we'll continue with the law of reflection and refraction in the next video.